Announcements. So your final exam is a week from Thursday. So what I'm going to try to do is talk about waves today and Thursday and have it wrapped up there. Your final homework 12, is already available. I think that's due Sunday. Does that sound right? Mm-hmm. In any case, I try to strike a balance between giving you enough time to finish it off after today's and Thursday's lectures on waves but also giving you enough time in the lead up to the final exam to take a look at the solutions and study other stuff. So we'll do what we can with waves this week. If there is anything that needs to get knocked off the end of the homework, I will announce that at the end of Thursday and then change those problems to 0 points. But as it is right now, homework number 12, roughly, reasonably, topics are in order from what I'll talk about first to what I'll talk about later. It's not going to seem like I got to that much today. You may only be able to walk away from today's lecture being able to do the first couple of problems. But a lot of it, we're setting the stage so that when we really get into things on Thursday, you'll be able to quickly see how all of it follows. So that's what we have. Homework 12 on deck. And in the next day or two, I'm also going to try to post the final exam practice materials, MCAT study materials, things like that. So they are there for you when you are ready for them. Okay, any quick questions before we get started? Admin or logistical? Yeah?
Will you be returning to teach the second semester?
At this time, I am scheduled to teach Physics 2, yes. Unless you guys would prefer somebody else?
No.
No. The rest of that question?
No.
Are you asking me, can I please not? Yeah.
Tuesday, next Tuesday, Thursday, right?
Yes, I'm going to just basically kind of just prattle on about various topics and try to draw some connections with all the things we've talked about, and you can jump in with questions if you have any at any point. But definitely can't be anything on waves at that point because the homework's already going to be due. And then I'll talk a little bit more about the final exam as well. But if you want to look in advance, all the information will be on the final exam practice materials going up soon. Anything else? Okay, so let's talk about a wave. Everybody kind of knows what a wave is until someone actually asks you, hey, what is a wave? I've never seen a wave. And then it's like, well, it's kind of like this. It's kind of like, well, and you kind of, at least for myself, I find myself at a loss for words for what exactly is a wave. Here's my best way to simplify it. It's a traveling disturbance. So if you have some stuff, as we call it, a medium, and you are watching some kind of disturbance moving through that medium, it's a traveling disturbance. It carries energy, but not matter. Okay? So it's not actually taking the stuff with it. If you need evidence of that, next time you go to shake out your carpet, okay, you go like this, get it so that whatever dust comes off of it, you will not find yourself accidentally shaking the pattern on your carpet off the end, right? So the stuff that the carpet is made out of is going to stay right there exactly where it is. You're just taking a disturbance and sending it from one end of the carpet. You're not taking actual molecules of the carpet, okay? So there are two types of waves that we'll examine, and the differences between them are largely cosmetic. We'll start with transverse waves. Transverse waves are probably what you think of when you see a wave. A transverse wave is one in which the disturbance or displacement of the material is perpendicular to the motion. So for instance, you might see a wave on a string, right? If you wave your hand and you make a wave on a string, the disturbance might move to the right while the disturbance is vertical. So there's a 90-degree angle here between these two. That's your classic transverse wave. An example is a wave on a string. Okay. There's another type of wave, which is also an important type of wave, which you may not necessarily think of as a wave, called the longitudinal wave. And this, my drawing is not going to do it justice, so I'm going to show you on a slinky, because a slinky is capable of carrying both a transverse and a longitudinal wave. If you wouldn't mind volunteering, I guess it's not really volunteering, hold the end of that. So a slinky can first do your classic transverse wave that looks like this. So you can see that the wave moves back and forth while the disturbance is vertical. And now let me show you what a longitudinal wave looks like. That is a compression disturbance. So I'll grab the thing like this. I'll pull back a couple coils and I'll go like this. And then you see a traveling disturbance of a different kind, right? So it's along the same axis as the motion. It's a kind of a compression disturbance. Thank you. So I'm going to attempt to draw that. Kind of looks like this. So region of compression that is traveling in a given direction. Let's say it's traveling to the right. And the disturbance is a compression disturbance. And it's along the same axis as the motion itself. This is an important type of wave because you're listening to a wave like that right now, sound waves, particularly through the air, are compression disturbances. So what I'm doing right now, the way that you are listening to me, is that I am creating with my vocal cords region of compressed air. Those regions of compression are traveling to the outside of your eardrum, and then the pressure differential between your inside your ear and outside your eardrum is creating vibrations in your eardrum that you are then going into your brain, and you are translating into what it is that I'm saying. Okay? So what we're going to do at first is look mostly at transverse wave just because they're easier to draw and usually easier to visualize, and then we'll realize that a longitudinal wave is not really much more different. It's kind of looks different cosmetically, but it's basically the same thing. The one thing we will not touch is water waves. The reason why is water waves are complex. They are generally transverse and longitudinal combined. So if you've ever gotten seasick, been sitting there in a boat, you kind of have this rolling motion, right? That rolling motion is a combination of a vertical displacement, that's your transverse wave, and your side to side, that's your longitudinal. So those two combined cause a rolling motion. So we don't touch water waves. They're actually kind of complicated. We can still talk about them kind of generally or conceptually, but when we really get down to the equations, we're not going to touch them. So let's draw a transverse wave. Our focus usually is what we call a periodic wave. So this is to distinguish from an isolated wave pulse that might be traveling all by its lonesome. We're talking about a wave that's regular and repeats. We call this a periodic wave. And the way that you might make this kind of wave, let's say this was a string. Let's say that the string used to lie right here. This is the equilibrium position of the medium, the string. If you want to make a wave like this, you can't just move your hand up and down once. You've got to do it over and over again on a regular schedule. So what you do is you take your hand and you move it in a periodic fashion. And you create regular disturbances that travel forward. So before anything else, let's just talk about the just general features of the wave. So what are the different parts called? Some of these are familiar from everyday English. The top of the wave is called the crest, just like the crest of a hill, okay, or something like that. That's the top, however you define as being the top. And the trough is the very bottom. Again, you hear that sometimes. That's used in everyday English. Of course, one person's crest is another person's trough. If someone's standing on their head, they might have a different opinion of what the top versus the bottom of the wave is, but it's still a useful reference. Let's talk about the physical dimensions. The physical dimensions of the wave, the amplitude is defined as the distance from the equilibrium to either extreme. So it's the distance from the equilibrium to a crest or the equilibrium to a trough. So that's amplitude, A for short. It's measured in meters. in SI units. And if this rings a bell, we talked about amplitude in terms of simple harmonic motion. It's the same deal. Okay? It's the distance from the equilibrium to the extreme. Please note that the total quote-unquote height of a wave, crest to trough, is actually 2 amplitudes. Not 1 amplitude, but 2 amplitudes. So that's the disturbance. How disturbed is it from the equilibrium? That is the amplitude. We can also talk about the physical dimension and the direction of travel. That's called the wavelength. So the wavelength, we use the Greek letter lambda. It's also a dimension. It's also measured in meters. And there, of course, if this wave repeats over and over and over again, there's no clear beginning or end. What a wavelength is not the total length, but it's the length of one repeating unit of the wave. So there's lots of different ways to define it. But the most important thing you're doing when you're counting a wavelength is to make sure you go from any part of the wave to the next exactly identical part. So one way to count wavelength is crest to crest. You get exactly the same result if you counted from trough to the next trough. I like crest to crest myself. I don't know why, but that's what I'll usually count. One mistake that students often make is they say equilibrium to equilibrium. That is not a wavelength. And the reason why is that even though the wave is in the same place again, equilibrium, it's not exactly reset. If you look at the wave, it's like this here and it's like this here. It's upward sloped in one place and downward sloped in another. What you have to do is you have to go to the next identical equilibrium. So it has to be identical in every way. And in fact, this original thing that I marked off here is only half a wavelength. If you're ever in doubt, if you have a wavelength, put it back to back. Make sure that it looks like the whole wave. If you put this back to back, you get this. That's not the wave. Okay? So those are the two physical dimensions of the wave, the amplitude and the wavelength. But that's not where the properties of the wave end. We have several other things to discuss as well. What we do is we put a fixed observer somewhere along here. Here's my physics eyeball. I don't know if I've drawn a lot of those physics eyeballs yet in Physics 1, but we'll do a lot in Physics 2. This is just a way to denote that we have a fixed observer somewhere, and we can ask what they see. So there are two things that they could measure. Actually more than two, but let's start with the period. That's the period of the wave. We once again have all these things popping up that are familiar from simple harmonic motion and other things. The connection to simple harmonic motion, as we will find, is not coincidental. It's very strong. So what is the period of the wave? What it is the time for one cycle to pass, right? That's the definition of period we've used, right? It's anything that repeats over and over, the period is the time it takes to happen once. In this case, the cycle is one wavelength passing. So it's the time for one wavelength to pass that observer. In other words, to pass a fixed point. So if you're like me, you prefer to count your wavelengths crest to crest. If you had yourself a little stopwatch, you'd start timing when one crest came by, you'd stop it when the next crest came by, and what you'd have there measured on your clock would be one period. Okay? Now, the other way to talk about the timing is to flip the question on its head and talk about frequency. Okay? So frequency is when you talk about, well, I'm not going to wait around for one full wavelength to pass. I don't have that kind of time. I'm going to wait here for exactly 1 second, and as much of a wavelength has a chance to pass in my 1 second, that's all I'm going to wait. Okay? So the frequency is the number of wavelengths, or number of cycles, I guess, that pass per second. Okay? So it's just a way of flipping the whole concept on its head, right? Rather than timing one wavelength to pass, I give it exactly 1 second, and I ask what fraction of a wavelength has a chance to pass in that time. The units here are per second. So they're inverse seconds, or as we call that, are hertz. And these literally are flipping the question on its head. These two are reciprocals of one another. So any periodic system, you can talk about the period, which is the time it takes one cycle to happen, or you can talk about the frequency, which is how many cycles happen per second. Okay? So it's just a way of flipping the question on its head. You can see the units themselves even are inverse. So that's the timing aspects if you put a fixed observer where the wave passes them. And then there's one final quantity we talk about, which is the speed of the disturbance. Okay? The speed of the wave. And so here's where we get into something that I'm not going to be able to justify entirely, but you're going to have to believe me, that the speed of a wave for us depends on the medium only. So if you want to know how fast the wave travels, you shouldn't be asking about what's the wavelength of the wave or frequency or amplitude or any of that stuff. You should be asking, well, what is the wave on? What is it traveling on? Is it wave on a string? Tell me about the string. Is it a water wave? Tell me about the water. It's the stuff itself that determines that. Now, for those of you that know a little bit more about waves, this is not strictly true. For instance, if you're a surfer, you know that waves travel at different speeds even on the same water. Okay? That is a particular thing to water waves, and it's particular to certain other systems. So I guess I'll put a little asterisk here just so I'm not totally lying to you. It depends on the medium only for relatively small medium disturbances. And I guess this sort of makes sense, right? If you have this massive wave coming through, that massive wave is such a wrecking ball to the medium that it'll literally change the property of the medium itself. Okay? So for us, we are going to assume that if you want to know the speed of a wave, what you need to know is about the medium. I'll give you one example of that, which hopefully will be convincing. Let's say you go to a rock concert or something like that, and you get the cheap seats, really far away from the stage. Okay? So sometimes you have the seats that are so cheap that you can visibly tell that the video is not synced up with the sound, right? You can tell the sound, as we'll see, travels relatively slowly, so sometimes there can be a significant time delay. Another example would be if you sit in the cheap seats at a baseball game, right? Then you see this, right? There's a delay between what you see and what you hear, right? So let's say you're sitting in the cheap seats at the concert there. You have all sorts of waves traveling at you. Music is not just there's lots of different waves that are in there, right? High frequency and low frequency notes, bass and guitar and all these other instruments. All these different waves with different frequencies, and yet they all, if they're all delayed, at least they all stay synced up, right? You probably never had that experience where the bass is out of sync with the guitar because you have the cheap seats. No one would pay for that concert, right? So why is it that all those waves stay synced up? Well, they're all traveling on the same stuff, the air. So if the air they're traveling on is the same, they will travel the same speed, and they'll at least be synced up when they get to you. So that's kind of evidence that the thing that determines the speed of the wave is the medium, okay? Not any particular properties of the wave itself, okay? So what we will do very shortly is we will develop these formulas which tells us about the speed of the waves, and we'll have to put in the properties of the stuff the wave travels on, okay? Before I do that, let me draw in some interrelationships between the variables so far. Let me go ahead and just apply good old distance equals rate times time. If If these waves travel at constant speed, we can apply distance equals rate times time. If you like, we use that for when we were having the horizontal part of a projectile motion problem, right? We didn't need to use all the constant acceleration fanciness because there's no acceleration, right? So let's see what we get when we apply that to a wave. Well, I'm going to say by definition, the wave moves by one wavelength in one period. That's just by definition. The wave travels over one wavelength in a time that is one period. Okay? So just for kicks, let me flip over to the frequency. So I'll replace period with 1 over frequency, and I'll solve, and I get this equation right here. So these three properties of the wave can be related: the speed of the wave, the frequency, and the wavelength. They have an interrelationship. I should mention at one point, this may not be true any longer, especially with the new MCAT, but at some point this was rated #1 most commonly applied equation on the MCAT. Okay? So let's talk about what this equation says. The first thing you might be saying to yourself is, I just got through saying that the speed of the wave depends on the medium only, and not on the frequency or wavelength or amplitude or anything else. And then here I come saying that the V is equal to frequency times wavelength. It seems like I've just contradicted myself. Okay? Well, it's not quite like that. This does depend on the medium only. It does not depend on frequency, wavelength, amplitude, any of that stuff. What this equation says is that once you have the speed of the medium, of the wave on a medium established, the frequency and wavelength are not independent. They are tied to each other because they always have to multiply to this fixed constant that's determined by the medium. So what it's saying is that if you have a fixed V, a high frequency wave will have a low wavelength, and a low frequency wave will have a high wavelength. So there is a very straightforward way to interpret that conceptually. So let's go through it real quick. So let me draw two waves for comparison's sake. So I'll draw a I guess I'll draw the large wavelength like this, and I'll draw a small wavelength like this. I'm going to pretend that those are identical media, so the V is the same. So the V is the same. And this one, since it has such a large wavelength, for some reason it has to have a small frequency. And likewise, since this one has such a small wavelength, it must have a higher frequency. Let's think about why that is. I'm going to sit here and watch the wave pass. And I'm going to snap my fingers every time I get a crest. Crest, 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 crest. And then I'm going to do it over here. And I get crest, 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 crest. It's a higher frequency. I get it more often, right? Why is that? It's not the wave is traveling faster. It's just that the crests are closer together. So that's why I'm getting them so often, right? So here, because the wavelength is small, the crests are closer together, that's why I get them more often. The frequency is higher. So that is simply the conceptual interpretation of what V equals F lambda means. It means that when the crests are further apart, or I guess I'll say crests are closer together, so the wavelength is low, you'll see them more often. So the frequency is higher. That is simply the conceptual takeaway that V equals F lambda says. It's just a way to encapsulate in an equation that when the crests are closer, you'll see them more often. That's it. That is why the frequency and wavelength have to multiply to a fixed value. Okay? Any questions so far? Okay, so before I go too long here, let me try to turn this thing on. Oh, I think it's warming up. So let me show you some wave applets. I posted these all for you. Some of them are a little cranky. They're Java, and Java has some security updates. It's annoying. So I wanted to show them to you in class as well. So here we have a applet which basically shows you a traveling wave. The wave is traveling to the right. So you see that the crest